Hi, my name is Patrick Adasa. This is James Adams, and Adrian is not here. This is our project that we're working on. We're working on the face and eye detection and tracking. So I'll let James talk about his part of the program, and I'll talk about my part of the program.
All right. A little overview of this presentation. We're going to talk about a little eye detection and color images based on chromaticity and geometric constraints. We'll talk about face detection using local hue and saturation histograms. And we'll talk about classification of eyes using Bayes classifier, as well as the final procedure for the entire eye detection and face detection, as well as some results and conclusions. The eye detection and color images based on the chromaticity and the geometric constraints are based on a previous paper here, eye detection and face images. It takes a color image, transforms it into the Y, CB, CR color space, and it's broken down into the individual Y, CB, and CR components, where Y is the luminance or the brightness of that image. The CB is the blue difference, where it's the blue minus the brightness, and CR is the red, or the red minus the brightness. The final product is an eye map and a mouth map that contains the eye and mouth candidates, respectively. The eye map is composed of two sub-eye maps, eye map C and eye map L. These eye maps are based on high CB or blue values and low CR or low red values around the eye region. The first eye map C takes a CB squared, and it takes also the inverse, and 2 is supposed to be a squared, sorry. This 2 here is supposed to be another squared, as well as taking the CB divided by CR components. For instance, if you had around an eye, if you had very high CB value, you'd have a very, square that, you'd have a very high number. If you took a low CR, inverted it, and squared it, you'd have another very high number. As well as taking a CB, a very high number, divided by a very small number, you have another very high number. So if you have a very high blue value as well as a very low red value, you come up with a very high peak for the eye map C. The next eye map L takes the luminance component, it puts it through a dilation and divides it by another erosion process. This one here is to ensure that we do not divide by 0 for an infinite value. After taking finding the eye map C and eye map L, they're multiplied together to come up with the complete eye map. The mouth map is based on the opposite, or strong red components and weak blue components around the mouth. The mouth map is used by the CR squared value subtracted by CR divided by CB, where this, I can't remember, eta or some Greek symbol is a eta. Okay, eta? Yeah, that's what I thought it was. It's a constant that's where you have each individual pixel of the CR squared component is summed up for an average divided by the average of the CR divided by CB, and it's giving you a total number to put into the mouth map equation. After solving that equation, we can get a general mouth map where all the high points are the possible mouth candidates. This is a picture here where all red points, if you can see, all red points are possible eyes for the eye map, and all blue points here are possible mouths for the mouth map. Now, this is one of the better ones. It finds virtually on the pupil itself, maybe just slightly below, and it also finds basically on the lower lip. Adrian was working on eye detection using local hue and saturation histograms. It basically takes a frame from the camera. It advances through that frame in large divisions, large squares. So for instance, we can take a frame here, take the entire frame and take a block, analyze that block, then take another block, analyze that block, and continually going horizontally, the next horizontally, until we analyze the entire face. The histogram is taken for each division, as well as the face, a sample histogram of the face taken previously. For example, we'll take that image, we'll crop the face out so we know what the face looks like, and then go through the process of scanning the entire image looking for that face. Both histograms are multiplied together, then the square root is taken, and all points in that histogram are added up. The highest sum corresponds to the highest correlation between the sample and the individual block that's taken for the entire picture. If we did some resizing, for instance, if there was a person could be far away, we could zoom in on that face or that detected region. If it was close, then it probably wouldn't zoom in at all. Here's the equation for the histogram. Again, we take the sample histogram, which is HS, multiply it by the current block that we're using, which is HF, multiply those together, take the square root, and then sum all of the individual points in that length of that histogram. Here is a histogram of the face. I believe this horizontal component is the hue, and the vertical component is the saturation. Again, this is a face here, and this is one of the blocks from the image where there could be a possible face. If you would have seen some points here, you probably could have established that there was a face in that block. Since there was not a very good match, it's probably that was probably taken during a point where there was no face in that image. Again, this is a skin tone, as well as taking the cropping out the face. We'll also crop out the a point on the face for skin tone to try to get a color and saturation for the skin tone for the face as well. Some of the problems, it's very slow. You can take smaller, you can overlap more on each block. Overlapping more is more accurate, but it takes a lot more time. I think that's taken by a threshold of how much overlap we take. It's slow. It requires a user sample of that face and skin, so you would have to go in manually, take a picture of your own face, or take a picture of yourself with the background, crop out your face, and then crop out a skin crop in order to do the entire process. It will also delete some points inside the face, as Adrian showed in the last presentation. For example, he had a face here, and for some reason it would take out a couple points here, a couple points here, and a couple points there. But essentially what we're talking about is it takes a full frame. He will crop out an image of his face, and then the histogram, the code will go through each component, or every so often grab a block and grab a block. For example, this worked really well, so it grabbed this block. It decided this block was the best match for his face, which obviously it is, and that's the block it took. Now, Patrick will go over the classifiers and PCA analysis.
Yeah, my contribution in this research was to build a classifier. This classifier was used for like verification purposes. My classifier was based on the maximum likelihood function. That's like the probability that a place of the face detected is actually like the thing that we're looking for. It's like an eye, a mouth, or anything that you're looking for. So there's a maximum likelihood function that I wrote based on the paper that I implemented. So for this function, you put like a class of data, like the probability that this class, like in this equation, I wrote a function for like a probability that like the probability that like the located part of the face is like a left eye. So the probability that there is a left eye is half of the data, the original data that we put in, and we find the mean of the data, and we transpose it. After that, we multiply it by the covariance matrix. Like I'm going to talk about how I got all my covariance matrix and the mean of the data using a PC analysis. That's what I'm going to talk in the next slides. So there's a maximum likelihood function that we use to detect like a place detected in the face. It's actually like an eye, a mouth, or anything on the face.
Well, in your likelihood function, why you only consider left eyes, not right eye. So
They just to illustrate for this function. So I can actually like put like different like I can actually like write a code for like a maximum likelihood function for right eye, for mouth, for eyebrow, and everything. So they just an example. Yeah. So to perform this classifier, like I have to take the data and perform a PC analysis. Like the PC analysis is basically to reduce the dimensionality of the data that I'm trying to detect, the data that I'm trying to analyze. So like I said, the PC is a powerful function for analyzing data. It's used to reduce the dimensionality of like the data and to verify or to perform your analysis on it. Yeah, so I'm going to walk you through like some of the pros that we the pros that we use for PC analysis. First of all, you can get a set of data or vectors, V of M. Get a set of data of size 1 by n. And after you get this data, you consider an array having another like a size of m by n. So after that, you compute the mean value of each column to obtain the mean vector. Then after that, you subtract your mean from the original data to get your adjusted data. After you find your adjusted data, you find the covariance of the original data, having a size n by n, because the covariance of every vector is a square. After you find a covariance vector, you find the eigenvector and eigenvalues of this covariance vector. After that, you use your eigenvector to actually like find your normalized vector, like there is the final data, and that final data is this right here. So this final data is a this final data is an eigenvector times the adjusted vector that we found earlier. Yeah, so some of the eyes that we collected to train our classifier, where like we use a camera to take an eye of Dr. Demetrius to train our classifier, and there's like a set of like 14 different eye vector with different locations and yeah different yeah. Okay. After that, yeah. Yeah, so after we get this eye, we use a PC analysis on it to actually like divide our eye into like set of blocks, like set of vectors. We convert our eye data to like a set of vectors. So that's it right here. So after that, we crop the region. We crop the region that we're trying to find. Like in this case, we try to find an eye. So we crop it and perform a PC analysis on it. So after we find our PC analysis, we put it into the classifier that already built earlier. So like if it's an eye, the probability that it's an eye is going to be like really like close to 1. Yeah. So that's the part that I did in this project. So I'll let James talk about the procedure for the face detection.
In our final procedure for the face detection, we'll find all possible eye and mouth regions using chromaticity, which in the image you saw earlier of red points and blue points. We also use region growing to eliminate large sections of eye and mouth candidates. So we'll take the assumption that the mouth and the eyes in that image are fairly small. So for instance, when we were in the lab, had a wall behind us and a brown door. And those brown doors and that wall would take up a whole lot of red points all around that wall. So what we could do is that instead of, and that point is being a peak, the highest point in that section. So we will expand that peak or that area around it. Maybe, there may be points of 0.7, between 0 and 1. So maybe 0.65, 0.7, 0.8, and it has that highest point of 0.95 or something like that. So we'll see. We can take all those higher points, 0.65, etc., make those 1, everything around it 0, so you have this white blob, this giant white blob. If that white blob is 1,000 pixels big, 500 pixels, or whatever we decide the threshold to be, we can eliminate it. So for instance, we'll eliminate that door section that has all those red or blue points. We'll eliminate that white wall that has all those red and blue points without eliminating necessarily the smaller points in the eye or the smaller points around the mouth. We'll also use hue saturation and the histograms to identify the facial region. Only regions that contain mouth and eye points are considered. If it, we'll take all blocks of the entire image, but if there's a block that doesn't contain any mouth points or any eye points, it's thrown out. After coming up with the top 2 candidates for the face, again we'll look for possible eye and mouths in that smaller region, and then we'll finally do geometric information based on the height of the from mouth to eye, angles created by the eye point down to the mouth, and finally distance ratios between both eyes and the mouth itself. We'll use those geometric constraints to determine are those eye and mouth point combinations a good combination to be a face. And finally, afterwards, after we come up with possible eye points, we'll use a classifier to verify if it's actually an eye point or not. For example, here's Adrian. The red box is the most likely candidate for a face. The blue box is our second most likely candidate. We took this because sometimes we would be try to stand perfectly still, take an image, it would show up on our face. And then we wouldn't change anything, take an image, and it'd show up in the top right corner as being the most likely for the face. We try to stand still again, it show up on our face again. Stand still, it may show up here once or twice more. So we wanted to see not only what the highest, what the chosen block was, but what the next chosen block was. We also just thought about maybe combining the blocks, because more than likely, most times, the blocks have a good overlap. But the blue blobs here are the chosen blobs, or the smaller blobs for the eyes. There's some more blobs. The green are chosen for the mouth. It's hard to see, but there's a small green section around his lower lip as well. So from those, the smaller section, we will look at the peaks of these blobs. Again, the red dots are the peaks for the eye blob, and the blue dots are the peaks for the mouth blob. We'll look at those points, and we'll do geometry constraints to determine, okay, maybe this is an eye, and this is an eye, and this is the mouth. Well, those don't match up too well geometrically, so we'll throw that out. This eye and this eye and this mouth, well, they don't match up geometrically either, so we'll throw those out. Then we'll finally look at this eye, and this mouth. Well, those look pretty good as geometrically, so we'll keep that in. We'll decide that that's the face. Here's Mike here. I think we've chosen either the eyes or the mouth to be blue instead of, or red instead of blue, so it looked really scary. So we changed that up. I think also we'll look at this in the problem section. I think he's holding the bag over his red shirt, because since we're looking at red points, that red shirt might have some problems. So I think he had some problems with his red shirt, so he used the bag to cover it up, but he didn't have as big of a problem, so I don't think he had to cover his up as much. So there's also a green point here as well. It's much harder to see. It's covered up by the blue. You see the maximum points in that section. It's not necessarily the centroid, but it's the maximum. So his maximum points on the eye and the mouth. come up with the correct face. Here's Dr. Demetrius. It also does not depend on facial orientation, so technically the face could be upside down and will still choose, it'll still do geometry and choose a section. So here's one where he's tilted sideways a little bit. Here's another one. And then finally here's one that doesn't work. It kind of picks up his eye. It's mostly closed, so it picks up his eyebrow instead. Here's me, a couple more possibilities. In general, the algorithm has satisfactory results. It's certainly not foolproof. It's got some problems. There's several thresholds that are manually operated as far as, like, for instance, the size of the blob is. Do we throw out blobs that have 500 pixels? Do we throw out ones that have 1,000? So we choose those, as well as what is put into the blob. Is 0.6 and lower made black, or is 0.7 and lower made black? Those are also things that are manually controlled, and it comes to the point where we can choose those for a specific person or a specific environment, but if you want it to work, not just in this classroom, another classroom for other people, it may have to be automatically chosen in some way. We may use automatic approaches, some probabilities to determine some thresholds. And future work for this coming REU, hopefully, we'll look at some automatic determination of parameters. We'll look at some background subtraction. For instance, if I'm, generally the background stationary, if I'm moving, then probably the thing that's moving is the human being, and look in that area, that moving area for the face. Operation time, we're going to try to work on becoming lower. I think it takes between 1 and 2 seconds for everything to operate. We'll also look at multiple classes for the classifier. Right now we're just looking at eyes. We might do ones for mouth as well. Also, I think it's just Dr. Demetrius' eyes that are in there, not everyone else's. So for instance, if he's in the image, I think the lower the difference, the better. So for his, it may look at a point of an eye and say, okay, that's -1. So that's a very good probability that that's an eye. And for other points, it may say that's -15, so it's not a very good probability. It's relative in that -1, -2 might be good for him, but if I go in there, -10, -12, -15 might be good for me, but points that aren't eyes might be -45, -50. So the difference between his and mine could be completely different, but still good picks for eyes. We also might consider some stereo imaging using 2 cameras for face detection as well. Any questions? Yes?
My little pocket Canon camera has face recognition that in the viewer, it'll put little boxes around faces. Do you know what kind of algorithm they use that's so fast?
I don't. I think it also, there was some papers we were reading, I'm trying to think what they used to determine an outline of the face. I can't remember what they used.
It's very, very fast, whatever it is. Inside a camera.
Yeah, it's pretty small too. Also, this was done using MATLAB. There might be C code or some other code that can make it faster, but obviously between 1 and 2 seconds, between milliseconds or tenths of seconds. Not too sure what they
I'd be
use.
curious what algorithm they're using.
Yeah, absolutely. Any more questions?
Roll back to the frame. Keep going. I'll ask you the question when you get there further back.
Oh. I didn't want to go back.
Good stuff.
It's stuck with me there.
That, yeah, that.
Okay.
Was that sampling but 4 squares for the view of the whole screen, the whole picture? You have a selection, of course, of how many squares you can select, right?
Right.
Like if you go across the upper left-hand corner and say, 1/5 of the width of the frame, and do 5 across, 5 down.
Right.
Is that are these pictures based on a minimal sampling of across the page?
Yes, there is a determination of what the size of that sample is, what size of that box is.
That's a parameter you set?
Yes, that was a parameter that is manually set by us, or
You
by
chose
it was
but
by
4
Adrian.
for the whole picture?
Yeah,
for-
it was, I
for
think,
just time?
well, it was, it was chosen based on the size of the image. I think 320 by 640 may have been a normal image for the webcam. Again, there's a lot of overlap. I'm not sure how many it actually takes as far as total blocks. But yeah, it's a manual setting that we chose based on time. Because if there's more overlap, I think it'll take a lot longer. Yeah.
Okay.
Any other questions? All right. Thank you very much.
Very good.
Okay, so that was the last presentation, and this was the first year of the REU. We had it through the regular